Okay, good morning, class. So today we're looking at probability. We're going to first mark the homework of yesterday. Not yesterday, sorry, the previous lesson, which is exercise 17.3. And exercise 17.3, it will, exercise 17.3 is on page 38, correct? At 385. 385. So let's look at this quickly. A dice is rolled. List the sample space. S. The sample space will be 1, 2, 3, 4, 5, and 6. Those are your outcomes. Use the set notation to describe the event E of obtaining an even number when the dice is rolled. So it's 2, 4, 6. Although 8 is an even number, I won't include it here because there's no 8 in the sample space. Okay. Let's look at number 3. Sorry, C. Use set notation to describe the event O of obtaining an odd number when rolling a die. So the odd, this is now for C, will be 1, 3, 5. Represent, now this is represent if obtaining a factor of 6. Okay, so looks like we're going to have quite a bit here. So let's put this here. So D, the factors of 6 is going to be 1, 2, 3, and 6. Okay. E, we are asked to represent the event if union O of obtaining a factor of 6 or an even number in set notation. So it's if union O, so it's or if or O. So what is in F is 1, 2, 3, 6. And in odd numbers, they have the 5 as well. Not so. So it's 1, 2, 3, 4 is not there, 5, and 6. So the only number not included in that is number 4. Not so. That is E. Let's look at F. F represents F intersection E. So this is F and E. So this is the element that belongs to both sets. So F and E is F, and here's E. So which number belongs to F and E? 2 and 6. So 2 and 6. Okay, that is EF. G. Make it a bit smaller. So G, we are asked to write down the number. I'm going to pull this up here. Now you ask in G, and change my color here, to write down the number of the sample space. So how many of the numbers are in the sample space? 6 numbers. Number 2, G2. The number in E Event E is 3. Number 3, the number of odd numbers, 3. Number 4, the number in the factor set is 4. The number of F union O, which I calculated in E, is going to be 5. The number in F intersection O, F intersection O. Now we worked out F intersection E. So we need to look at F intersection O. So how many numbers are overlapping then? 1 and 3. So it gives you 2. This is represent the set S, E, O, and F as a single Venn diagram. As a single Venn diagram. So I start off with the sample space. Okay? Sample space. And we know that it's a three-way, there's 3 events happening, not so. So is event E and O joined? No. That they are disjoint. Can you see that? Why? Because there's no element that belongs to O and E. Can you see that? However, E and F is joined and O and F is joined. Not so. So, if I draw this, the one that is joined to both is F. O is disjoint from E. Okay. So we fill in our even numbers. Our even numbers that are also factors of 6 are 2 and 6. E and F is 2 and 6. F and O, 1 and 3. So what is left of F?
Nothing.
So there's nothing left of F. Not so. Then, what is left of O? 5. Of E? 4. 4. So what is not accounted for is 1, 2, is 1, 2, 3, 4, 5, 6. So all is accounted for. Can you see that, people? So there's my Venn diagram. Okay. Let's look at the next one. Number 3. Odds. So in number 3, we are told that all the odds are taken from the pack of cards. All the odds are taken from the pack of cards. These cards are shuffled and one card is chosen. List the sample space S for this experiment. So all the odds cards. So how many odds cards are there? 30. So you're going to look at the sample space here. It's going to be, S will be 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, and Ace. Okay. List a set to represent the event P of drawing a picture card. Okay. So the picture card here would be Queen, Jack, King, and Ace. It's not Joker, it's Jack. Joker is a different card. Okay. Look at C. C says List a set of numbers, list a set for the event N of drawing a number card. Okay, so N would simply be 2, 3, 4, 5, 6, 7, 8, 9, 10. Right. D. Represent SP and N on a Venn diagram. So the sample space. Is there any elements that belongs to set P and N? No. So they are said to be disjoint. Also known as mutually exclusive. They are disjoint and also known as mutually exclusive. Okay. Alright, next question. So for E, they want to know list the number in A and N. That's going to make this a bit bigger. I'm going to redraw that subset in, because as you can see, there's a couple of questions to follow. So that was 2, 3, 4, 5, 6, 7, 8, 9, and 10. Again, it doesn't have to be in that order, it can be jumbled up and so on, as long as it's in the set. So E1, the question says list. Now here it's list and is a number. They either must tell you list P and N, or they ask you for the number P and N. Here they ask you both. As you can see, for P and N, we must look where it overlaps. Is there any overlapping there? No. So the answer is 0 if it is number. If the question was what is the number of P and N, it will be 0. But if they ask you to list P and N, that would simply be an empty space or a 0 with a line through it. You see the difference? That's why they can't ask you to list the number. Okay? There's a difference there. Let's look at number 2. Do the set P and N have any elements in common? The answer is no. What description of set P and N is suitable? They are, or you can say they are mutually exclusive. Okay. Then it says show that the number of P or N is equal to the number. Alright, so there's an identity we need to prove. So if the left hand side of the identity, the number of P or N. P or N. So what we're going to do there is, it can belong to set P or it can belong to set N. Or. Okay. So that means to say it's all of these here, not so. Which means to say how many of them are there? 30. You see that? Now we go to the right hand side, RHS. The question says the number of P plus the number of N minus the number of P and N. Okay, so how many elements belong to set P? 4. How many elements belong to set N? 9. Minus the elements that belong to P and N, which is P and N. 0, which give an answer of 13. You see there? So what do we notice? 13 is equal to 13. Can you see that, people? So how do we answer that question? We say therefore Therefore, either left hand side is equal to right hand side, or in the number of P or N is equal to the number of P plus the number of N minus the intersection of P and yeah, just prove that identity now as well. Okay. Let's go to the next question. Tan D has a bag containing 3 red, 4 blue, and 6 green. So she has 3 red marbles, 4 blue marbles, and 6 green marbles. The bag is shaken and a marble is withdrawn. The color of the marble is noted and the marble is replaced. Which means to say the marble is put back in the bag. You guys understand? So that's the sample space is for this experiment. So what would the sample space here be? So we'll have how many red marbles? 3 red marbles. So we call marble 1, marble 2, marble 3. But they're the same. No? How many blues? 4. They're the same. So if I draw any one of those, it will be considered as the same marble, blue. We've got 6 green. 1, 2, 3, 4, 5, 6 green. So 6, 5, 4, 3, 2, 1. Okay, this is the sample space. Okay. Let's look at B. Express the event of drawing a green marble in terms of a set. So G would be G1, G2, G3, G4, G5. I see you all can count to 6, well done. Okay. Go to the next question. List is set to represent the drawing either a red or blue marble. Red or blue. So it's a red union blue. So it's going to be R1, R2, R3, B1, B2, B3, B4. Will you guys understand? Is there any confusion at this point? Right. D. List. It shouldn't have been list. It should have been just determine or calculate. No? I think. Maybe I'm wrong. Let's look at D. Number 1. The number in S is what? How many marbles are there in total? 30. The number in green is 1, 6. Right. Number 3. The number in B, blue or red. So it's going to be 1, 2, 3, 4, 5, 6, 7. Right, you want to go with that, people?
Yes, sir.
Okay. He didn't ask you to draw a Venn diagram here. Boring. Right, let's look at number 7. Number 7 says, cards number 1 to 12 are placed in the hat. The hat is shaken and one card is then drawn and replaced. The card is taken out and is put in back. There's the sample space. So the sample space here would be 1 to 12. Okay, B. List is set to represent the event A of drawing a number with a factor of 12. 1, 2, 3, 4, 6, and 12. C. C says, list the set to represent event B of drawing a card numbered with a multiple of 4. Multiple of 4 is 4, 8, 12. G. Represent A, B, and S by means of a Venn diagram. Okay, so I'm just going to draw it here. You can see that it's right behind the calculator there. Right? Did you guys get it?
I feel like it's to be less than too much. Carry on.
Okay, so which elements belong to set A and B? 4 and 12. So there are two elements that belong to the both sets. Not so. So are they joined or disjoint? Joint. So you have got A and B. 4 and 12 is in both sets. So what is remaining in set A only? 1, 2, 3, and 6. What belongs to set B only? 8. But remember the sample space is numbers 1 to 12. Have I counted for 1? Yes. 2? Yes. 3? 4? 5? No. 6? No. Yes. 7? No. 8? Yes. 9? No. 10? No. 11? And 12? Yes. Alright. That is D. Another question here? Yes. E says, in question E, please settle down if you don't mind. Hey. E. They ask you the number in S. How many is in S? 12. That's number 1. Number 2. The number in A. 1, 2, 3, 4, 5, 6. The number in A is 6. Number 3. The number of elements in B is 3. 1, 2, 3. Number 4. The number in A and B. A and B is 2. A or B. So it's basically the union of. So A or B. So that would simply be 1, 2, 3, 4, 5, 6, 7. 7. Okay. 9. 1, 2, 3, 4, 5. So it's 7. You see 5 is on the outside. Which means it was 1, 2, 3, 4, 5. 5 plus 7 is 12. So it gives you the sample space. Later on we'll speak about complementary events. Okay? Then it says again, show that. Okay, so let's just get the purple here for F. So it's going to be the number of A or B is equal to A or B was 7. The number of A plus the number of B minus the number of A and B. Okay, this is the left hand side of the identity and this is the right hand side. Okay. So the number in A is 6. The number of B is 2 minus the number of A and B, which is the overlap here, which is 2. And what is 6 plus 2? 8 minus 2 is 6. the number in A is 1, 2, 3, 4, 5, 6. The number in B is 1, 2, 3. Where did I get 2? The number in B is 2. The number in A and B, that is 2. The answer is 7. So therefore, the number of A or B is equal to the number of A plus the number of B minus the number of A and B. Okay? Yes? Yeah. That's going to be your identity. That will be applicable all the time. It will work all the time. Okay? That's your probability formula. Okay? So now we're going to look at calculating probability. And this is exercise 17.4. It's for exercise 17.4, which is on page 389. This example is on page. I'm reading from page. Okay, so we are looking at calculating probability now. The outcomes that has an equal chance of happening are called equally likely outcomes. For example, when you throw a fair, unbiased dice, so many a time we spoke about when we introduced this, or we start this topic, we said that if we're going to calculate the probability of a dice or cards or things like that, we're looking at the case where it is fair. Unbiased means to say it's basically equally likely to land on anyone. Okay. So, for example, when we throw a fair or unbiased dice, each of the outcomes in this outcomes in the sample space would be 1, 2, 3, 4, 5, and 6 is equally likely to occur. Okay. When all the outcomes of an activity are equally likely to happen, we can calculate the probability of an event E happening by using the definition. So you need to write this down. The probability of an event happening is equal to the number of favorable outcomes over the number of possible outcomes. Okay. Which is also the probability of E, an event happening, is equal to the number of elements in E over the number of elements in the sample space. Okay. So let's look at the example, and this example is on page. Same page, okay. So when you throw a dice, the possible outcomes are numbers 1, 2, 3, 4, 5, and 6. So the number of the sample space is 6. Can you see that? This is called the elements in the sample space, is 1 to 6. Okay. So event of getting a 4. So the probability of getting a 4. How many 4s are there? So the number of 4 is 1. So we know that the probability of 4 is going to be the number in 4 over the number of the sample space, which is 6. So how many 4s are there? 1 out of 6. You guys understand? So you can say it's 1 out of 6, or you can say 1 over 6. And you can write it as 0,1666 or 0,167 or 0,16 recurring, or you can write it as 16,67. Okay. So in an exam, you have the choice to give it in any of those 3 formats. Either in simplified fraction form, in decimal, or in a percentage. Okay, all of those is acceptable. Okay, so you can decide which one you want, which way you would like to write it. Okay. Let's look at event 2. Event 2 of getting a number more than 2. People, what is the sample space for more than 2? So the number more than 2. What are my options here? 3, 4, 5, and 6. And how many outcomes are there? There are 4. Not so. There are 4 outcomes. So the question says when you work out the probability of getting a number more than 2, will simply be the number of elements more than 2 over the number in the sample space. Can you see that, people? So how many values of how many elements are more than 2? 4 out of 6, which is 2 out of 2. 2/3 can also be written as 0.6 recurring, or 0.67, or 66.67%. Okay. Let's look at the next one. Look at number 6. Event 3. Getting a number more than 6. A number more than 6. So is there any numbers on the dice that is more than 6? No. So the number is 0. So the probability of a number greater than 6 is equal to the number greater than 6, the number of elements greater than 6, over the number of elements in the sample space. So it's 0 over 6, which is 0. So that probability is 0, which means to say it will never happen. Okay. No, that even 0, the line through it, means to say that the set is empty. It's an empty set. Yeah, they asked you for the number. They didn't ask you for the elements. Because your element, 0 can be an element of a set. You understand? 0 could be an element. That is why I wouldn't put that in here. Okay. When we're talking about in the list of things like that. Okay. People, event 4. Is it Kanya, my girl? You're sitting far from me today, so you're falling asleep. Huh? Right. People, getting a number less than 10. So how many elements are less than 10? There are 6. How many elements are there in the sample space? 6. So the probability of numbers less than 10 is going to be 6 over 6, which is 1. So it's certain that when you throw your dice, it will be a number less than 10. You understand? Right. Right. Let's look at the next question. This is on page 368. 386 only. 386. So here we are told that there are 12 boys and 18 girls in the class. There are 12 boys and 18 girls. Okay. So if each boy is coupled up with a girl, there's 6 girls surplus. No? Extra. Okay. Yes. Sorry? Page 88? Yeah. Sorry about that. 88. Okay. A learner is chosen from this class. What's the probability that a boy will be chosen? So again, how do we calculate the probability? The probability of an event is equal to the number of the event over the number in the sample space. Not so, which is also the probability is equal to the number of favorable outcomes of the number of possible outcomes. Okay. This is your probability formula. So they want to know what's the probability that the boy will be chosen. So how many boys are there? 12 boys. And how many boys are there in the, how many children are there in the sample space? 30. So the probability of boys is equal to the number of boys over the number in the sample, which is 12 over 30, which is 12 over 30 is 2 over 5. It's also 40% or 0.4. Okay. See any confusion there? Zoe? You okay, my girl? Don't talk to that one. Your name Amber? Why you change your name? Okay. Alright. Is Zoe your sister? You look like her, Zoe. Okay. This one we have already. We did already. Let's look at this one. Right. A letter is chosen at random from the word classroom. What is the probability that this letter is, in the first case, a M? Okay. So again, people, how do we calculate the probability? It's going to be number of favorable outcomes over number of possible outcomes. So, how many M's are there? 1 M out of 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 letters here. So it's 1 out of 9. B. The probability of drawing an O is going to be equal to the number of O's there are over the number of letters in the sample space. There are how many O's? There are 2 O's. 2 over 9. Okay, C. A vowel. Now what are vowels? A, E, I, O, U. Okay, it's the only thing I needed to know about English. Okay. So that we can answer this question. Otherwise, what's a verb? What's a noun? I don't know. But anyway, there's an A and 2 O's. So it's going to be 3 over 9, which is. Okay, I feel like I'm moving too slow here for you guys. Because you are making jokes and you're talking your own conversations in the background. Just stop it, please, man. It's irritating. Every day I must tell you the bloody same thing. Okay, so now we're told on page 388, probabilities can be calculated either by theory, which we're doing now so far, or by experiment. Experiment is basically when you're doing it in real life. Okay, so when we toss a coin, by theory, it can either be a heads or a tails. So the probability there is, if it's heads, it's 1 over 2. But when I toss a coin as an experiment, I'm not going to toss 1 heads, 1 tails. 1 heads, it doesn't work like that in reality. Not so. However, if we do it 1,000 times, maybe 550 times will be heads, and the others will be tails. It won't be 50-50. But the more you do it, the closer you're that experimental, or your frequency will resemble true probability or your theoretical probability. Okay. So let's see here. The theory method relies on logical thinking. The experimental method relies on repetition of many trials. Trials is basically flipping the coin or rolling the die. Okay. For example, suppose you want to find the probability of getting a hit when tossing an unbiased coin. What does unbiased mean again? Fair. Okay. Theory method. Unbiased means that both events heads, tails are equally likely to occur. There are two possible outcomes, is heads or tails for the sample space. The numbers for the sample space is going to be 2. There is one favorable outcome, E, for heads, 1, or tails is 1 as well. This is my problem. Yeah, that is it. Okay. So suppose you're getting a hit, of course it's going to be 0.5 or 1 out of 2. Okay. Experimental method. Suppose you toss an unbiased coin 100 times and count the number of hits you get. Suppose you get 49 hits. The relative frequency. Now here we talk about the relative frequency is going to be 49 over 100 or 0.45. Relative frequency gives us a good value for the probability, but only after many trials. Okay. So the more trials you do, the closer to theoretical probability you'll come. Okay. Here we are told that relative frequency is equal to the number of favorable outcomes over the number of trials. So it's how many times you're actually tossing the coin or rolling the dice. So that basically brings us to exercise 7.4. In 7.4, I want you guys to do the following numbers. Number 1, number 3, 5. So it's basically the odd numbers. Okay. So at this point, we'll stop the video.